Yeah, actually, of all places I found in our department library a book by Bernoulli, Hydrodynamics. Normally we don't have access to the old work because they're written in foreign languages and very few of us know Latin or French and so on. But Professor Hunter Rouse got two graduate students to translate the books by Johann and Daniel Bernoulli into English. And for some reason, one copy of the book is in our library, Dover publication. So there, he's given the reason which seems reasonable, why the water surface is not inclined. Suppose it was inclined, then you take a slab like this. Then there is weight acting and there is force due to pressure there. But since the column is at rest, there cannot be any shear stress opposing that. So, sorry, I should draw it another way. So it cannot be like that, it must be flat. That's the reason given Bernoulli. There may be other reasons involving surface function and so on, but that seems reasonable. For the sand, only difference is it can have shear stresses, so it can form slope. Of course, there is a limit to the slope it will form. Suppose you call the steepest slope angle phi. You can imagine, suppose you put a particle here. If you make it steeper, the particle rolls down. So there is a limit, and some physicists have calculated for glass bead, smooth glass bead, about 23 degrees for spherical pipe. Now please ask question if something is not.
What?
Sorry?
What in this case determines the flow rate?
That's a difficult one because that's limited. Unfortunately, board is only one side, so those are behind. See, for a long time, people had looked at flow through horizontal orifices. It means things like see, this bottle, this had a hole at the bottom which had now closed. So if you had a hole, you could try to estimate the flow rate of sand through this hole. And what they form, we call this opening D. Let's say it's circular opening. So there is a famous correlation by Beverloo and co-workers. 1961. You say that the velocity here scales as square root of gd, where g is acceleration due to gravity. It just gives a velocity scale. There is no reason why it should scale like this, but since we find that flow rate is independent of the head of material, that is the flow rate from this hole and this hole roughly equal if you measure it. So then you may think D is a reasonable choice of scale. Of course, another length scale is the particle diameter d. But suppose d is much greater than dt, we expect this to be velocity. So once there is a velocity scale, mass flow rate m dot that will be area into velocity, that's the volumetric flow rate into some density. So the area is proportional to d squared. So this will be proportional to square root g d power 5 by 2. D square and d power. And roughly it matches with experiments. Except one correction introduced by Beverloo, that instead of d you replace it by d minus a d. Where k is a constant, dp is a particle length. K is of order 1. So this is a correction for finite side reference. For water flowing through a hole, normally we don't have to worry because the size of the molecule is so much smaller than the orifice size. But lab experiments in powders, this d by dp may be 20, 30. You could have much bigger sizes, but the flow rate is so high that you need large amounts of material to be transported to and from the storage area. Any other? No, I'm not finished with this.
Did you not say that the peak of the continuum
the width of the container. Not much, only the hole. So Raghuram, again, now I have to fill this. Yeah. You use a funnel. So if it behaves like water, you will expect the flow would not be very good. But you see, it will flow almost the same way. Because the medium is permeable to air. So while the particles are falling out, air is going in. So it equalizes the pressure and then no problem. Now we'll do the same experiment with water and you'll see some funny things happen. Now we have to close this hole. It's already closed. Just fill water, both arms. Fill water from this. Jump now. Okay. Yeah. Okay. After a while, the flow will stop, hopefully. It's open. Very thin jet. Yeah, see now it's stopped. Some leak may be there, little bit. Now the fun starts, we open both. Before I do that, can you tell what will happen? Suppose I open both the holes and the cap is closed. What will happen? Anybody will Yes. And the upper one? Yeah, bubbles. So sometimes it doesn't work. Now you see, it's hardly flowing. So now both holes are open, but very flow. It may depend on how we close this. Sometimes you can get bubbles. Yeah, I can see one or two bubbles flowing. You have to wait for the while, you may see occasionally. Okay, Kappan is open actually. Occasionally you can see bubbles. But, once there was a continuous stream of bubbles, maybe the orientation. Yeah, it is small hole, but you will see sometimes bubbles. So that's another difference between the flow of water. Now coming to the question about flow rate, similar correlation is not available for this vertical orifice. So people have worked on this horizontal one for a long time, even before 60s. The vertical one, only one or two papers are there and some empirical correlations which don't match very well. This Anup Sharma, who was a summer student, he had done some work. So here correlation proportional to D or D.3. Now it's not clear how this number is coming about, and this is a dimensional correlation. Of course, he scaled it by some nominal diameter, but not very satisfying. So in fact, if some of the people here who work on granular materials, what a nice problem, look at this. The only hesitation I have, it's difficult to find applications for this flow from vertical on. So you may be short of if you send papers. Difficult to find any application. But very interesting problem, and the flow is also quite interesting. Because we have a system like this. The material flows out. If you watch it, there is some region here which is almost dead, and it forms its own internal bond. So to predict this using existing theory is very difficult. Another thing I want to say, whatever experiment you are doing, very close to that, there will be a small change in configuration, which behaves very differently. But you may work on it for years and not think of that configuration. For a long time, I have not even thought of looking into vertical. Always focusing on horizontal. We tend to go into groove and just stay there. Okay. Now we'll go to next. This one. Okay, you have to wait until 4 hours. Yeah. See, now it's open and the hole is also open. But very little is coming out. The reason is, this was pointed out in this paper by Oliveira. Actually, I been to this paper some time ago, and we set up the experiments for our experiments course, but never read all of it. So when I was discussing with my colleague Professor Gandhi, we happened to read it, and he said, you know, after some time, the flow stops and nothing comes out. And you can guess why it doesn't come out, even though the head is non-zero. Surface tension. So the surface tension, I have some numbers which the summer student has calculated. Let me just put it. So the diameter of the hole is V, and the height will stop. That height is 8. Next one. Sorry, 11. So as you expect, as the diameter increases, the head decreases. Now suppose you want very crude models for this. We just take this hole and assume some drop is just on this. Okay? And this is the height. So we balance the pressure head with surface tension. Theta is the contact angle from this vertical. So that's theta. And the surface tension is gamma. So gamma into the component in the horizontal direction, which will be, this angle is 180 minus theta. So gamma sine 180 minus theta into the circumference, which is into pi d. That should be the area pi d squared by 4 into the head. Measure. So if I erase all this, I'm sorry, the magnet is coming out. So anyway, H will be 4 sine theta. So we can calculate with this. The problem is what value of theta to use, contact angle. Professor Gandhi said theta may be quite large, but today I could not find time to check on the internet. Anyway, suppose you just fit it to this, we will get theta about 130 degrees, which may or may not be reasonable, but we will get the order of magnitude and the calculate value. So I forced it to fit here, so that's close, but here it is decreasing a bit. Okay, you can get order of magnitude. If you want more accurate thing, then probably a lot more careful analysis. So now one thing I wanted to share with you, the experiment has been done by 4 batches of students each year for 3 years. So that is 12 batches, each batch 3 students, 36. No one has reported this stops. Why? Because the goals of experiment have been defined. We measure the flow rate. So the focus is on the flow rate. So while trying to do one thing, you may not pay attention to the other things. I have also not noticed till Gandhi told me these authors have worked out. I am sorry, the cap is...
Did you try to take a picture of that?
Sorry?
Did you try to take a picture of the bubble there?
No, it's very small hole. We will not try. We can try. Sorry? Calculate value.